Hello guys, welcome to my channel Algorithm Avenue. In this video, we'll be studying what is perceptron trick and the problem with perceptron trick. Okay, now let's see what is a perceptron trick. Now let's suppose say this is some set of data points and these are some set of data points. This is one class and this is one class. Now there's a binary classifier which draws a line separating both this data points. Means it's separating both these classes. Let's say this is a geometric boundary. This is a geometric boundary. Now this is a geometric boundary separating both these classes. Okay. Now how this boundary is drawn? As in the previous video, I have said you what happens is let's initially say this is our initial binary classifier line. Now what happens is now let's consider this point. This point asks this binary classifier line whether I am classified correctly or not. Means if it is not correctly classified, means it is misclassified. What happens is according to this data point, our binary classifier moves. Okay, now it has changed to this. Now it asks, let's say here is another data point. Now it asks this data point whether, means randomly it is selecting some data points and asking each data point whether it is correctly classified or not. Means now it has asked this data point. Now this data points checks with this line whether it's correctly classified or not. Means when it's not correctly classified, according to this, our line is altered. Okay, in this way, adjusting the binary classifier line, having a means adjusting this binary classifier line as our geometric boundary to classify two different classes is called perceptron trick. Okay, what you just saying you what we have seen in the previous video. Okay, now just what newly I said is we are naming that method as perceptron trick. Okay, this is perceptron trick. Now let's see what is the problem with this perceptron trick, so that we have to go with the loss functions. Okay, now let's see what is the first initial basic problem of an perceptron trick. Okay, now let's say uh, this is our first classifier line and this, let me rub out this. Okay, I have rubbed both these lines and this is our next classifier line. Okay, can you determine which is the best binary classifier, means which is the best fit line to classify both this data? You cannot determine, right? Both are both look similar and both are used for binary classification. Both are dividing equally the this data set and this data point, this set of data points and this set of data points. Means you are unable to determine which is the best fit line. So what a loss function does is it will try to determine which is the best fit line. Okay, now this is the first problem with our perceptron trick. What is the first problem with perceptron trick is when you have multiple binary classifiers, it will be unable to determine which is the best binary classifier. Okay, this is a first and basic problem of an perceptron trick. Now let's see another problem with the perceptron trick. Now initial stages of training, you'll be having the binary classifier line here. Okay, now let's say you have chosen, means your model has randomly chosen this data point for adjusting an binary classifier as a best fit line. Okay, now let's take an hypothetical scenario where each time your model, means when you set to your condition to 1000 times it asks this data point whether I am correctly classified or not. 1000 times this data point says and yes, you have perfectly predicted that I am correctly classified. Okay, means what happens, the line never gets altered, means line never gets to its perfect position. So it will, now you see that there are n number of misclassified lines. Means what is the second problem is when you choose and correctly classified data point, means each time you choose a same data point for your class, means for your binary classification problem, what happens is your binary classifier line never gets to an best fit line. Means this binary classification line never becomes a geometrical boundary for and two classes data set. Okay, this is the first this is the second problem of our perceptron trick. Okay, the first problem is when you have a number of best fit lines, you cannot determine which is the best fit line. The second problem is when you choose an correctly classified data point, each time for moving means for altering your best fit line to be as a geometrical boundary, your line never gets moved, and you have that misclassified data as it is. So when you have this misclassified data as it is without being moved, means you have very much means your model is performing very much poor. Okay, these are the two basic problems with perceptron trick. Okay, in the previous section you have seen that the problems with perceptron trick. Okay, the first very basic problem is it when you have multiple binary classifier lines, it is unable to determine which is the best binary classifier. The second problem with perceptron trick is when each time model chooses a single data point randomly for classification, means to adjust this binary classifier, it's getting failed. Means it is just it is unable to converge to its original position. So these are the two basic problems with perceptron trick. So to encounter this, what we introduced is loss functions. Okay, generally what we do in machine learning is we don't use these kind of tricks. Okay, these kind of tricks will never perfectly work in each kind, means in each data set of each model. Okay, so what we need is a consistent method that can work for any dataset and any model, which can produce us some best fit line, which can produce some geometrical boundary that can best able to classify two classes. Okay, so for that we have introduced loss functions. What these loss functions do is, suppose you say you have two different binary classifier lines. Okay, it assigns, what this loss function do is it assigns an integer value to each of the binary classifier lines. Okay, let's say first it has a, for first binary classifier line it has assigned 21 value, and the next binary classifier line it has assigned 23. Okay, this is a numerical value to corresponding to this line, and this 21 is a numerical value corresponding to this binary classifier line. Okay, now to determine which is the best binary classifier line, means which is the best geometrical boundary to classify this both classes, is which has the least numerical value. The line with least numerical value is determined as a geometrical boundary of two different classes. Okay, what is this numerical value is, it's loss. Okay, when the loss is minimum, your model is performing really well. When the loss is high, your model is not performing really well. Means these loss functions also determine magnitude of the model performance. Means how less the loss, that good the model performance. How more the loss, that less the model performance. Okay, now let's see some basic method to calculate the loss. Okay, the first method is, okay, this is the data set, means these are some set of data points, these are some set of data points. Let's say at some stage of training your model resulted as this binary classifier line. Okay, now in the first method how we calculate the loss is we determine the number of misclassified points. Now in this case actually these points must be lesser than this binary classifier, but in this case means in this case of in this set of parameters corresponding to w1 w2 and b, this is your binary classifier line. This binary classifier line has misclassified these data points incorrectly. Means the loss of this uh, binary classifier is 1 plus 1 plus 1, 3. Now let's take another condition where you have new set of w1 w2 and b values and your binary classifier line is this. Okay, now let's see how many data points are misclassified. Now let's erase this. Now this is not your binary classifier line, but this is your binary classifier line. Corresponding to this, these are your weights and bias value. Okay, now let's see how many data points are misclassified. Now for the second set of second binary classifier line, the loss is calculated as number of misclassified data points. This is first misclassified data point, this is next misclassified data point. So 1 plus 1 is equal to 2. Okay, this is the first method to calculate the loss. In the first method, what we do is we'll be considering number of misclassified data points. We'll count the number of misclassified data points and we'll be calculating the loss. Okay, now let's see what is the problem with this first method, so that we have jumped to the next method. Okay, in case of first method, let's say you have outlier. Okay, let's say even this data point is also misclassified. Okay, now for each data point, for each misclassified data point is having some corresponding magnitude. Okay, now for this data point, means this data point is nearly correctly classified, means it is at the boundary, means it is at the boundary, means if it gets little adjusted, you will get this data point classified correctly. But this data point is difficult to classify for the model, but this is given equal magnitude, means all these three data points are given equal magnitudes. Okay, the data point that is misclassified and it is nearer to the geometric boundary is given the same magnitude, and the data point that is lying very much outside, means very much distant to the geometric boundary, is also given some equal data point, equal magnitude. So now how model will understand that means how much error it made. Okay, when the magnitude, means when you have equal magnitudes for all misclassified lines, how your model will be able to understand how much error it made. Okay, if the model knows how much error it made, it can adjust according to that, and means adjust to that and give some perfect best fit line. But in case of this, as each misclassified data point is having same magnitude, you cannot determine, means you cannot determine how much the model, means you cannot determine how the model understood this set of data points having the equal magnitudes and adjusted its binary classifier line. Okay, this is the main problem with the first method. Okay, now let's see the second method. Second method, let's say this is an this is some data point and this is some data point. You are having just two data points, but this data point is misclassified, this data point is also misclassified. Among these both these data points are misclassified. Now in this second method, what you do is you calculate the perpendicular distance from the line. Okay, the perpendicular distance from the line is calculated, means from the misclassified point to the line, you calculate perpendicular distance for this first data point, and second, for this second data point you calculate the perpendicular distance. Okay, now when you add both these results, the resultant is your loss. Okay, when, means similarly, when you have any number of data points, you calculate from the data point to the line perpendicular distance. Okay, from the data point to the line perpendicular distance, and you add up all those distances, and at the end what you got is your loss. Okay, now let's say this is one misclassified line, this is one misclassified point, this one misclassified point, this one misclassified point. Now the perpendicular distance is 6, now perpendicular distance is 7. Okay, when you add up this both, loss is equal to 6 plus 7 is equal to 30. This is your loss. Okay, similarly, when you have n number of data points, you calculate the similar. Now what is the problem with this second method is calculating the perpendicular distance is a little complex. Okay, is a little complex operation. So in short, what we did is we introduced the third method. Okay, now let's see the third method of calculating the loss. Okay, take similar data set where you have 2 points. This is one point, this is a binary classifier, and this is the second one. These both are misclassified data points. Okay, now we are discussing about third method. Okay, let's say the equation of this line is 2x plus 2y plus 4 is equal to 0. Okay, this is the equation of this binary classifier line. Okay, now the data point, this misclassified data point coordinates are, let's say, 4 comma 2. Now this misclassified data point coordinates are -1 comma 2. Okay, now what you need to do is, for the first data point, means for the first misclassified data point, you need to substitute these coordinates in this equation, in this line equation. Okay, first substitute this 2 into -1 plus 2 into 2 plus 4 is equal to 0. Okay, now you need to substitute these data points, and you have to calculate the resultant value. -2 plus 4 plus 4 is equal to 0. Then you will get 6. Okay, for the first data point you got the numerical value as 6. Now substitute the second numerical value. Okay, when you substitute the second set of data points coordinates, 2 into 4 plus 2 into 2 plus 4 is equal to 0. Now calculate the numerical value. 8 plus 4 plus 4 is equal to 16. Now add these both the results. Loss is equal to 16 plus 6 is equal to 22. This is your loss. Okay, in this method what you do is some simple operation. First you need to have your line equation, then the coordinates of the misclassified data points. Now substitute each coordinates in this line equation and calculate the resultant values. Now add these resultant values and you will get the loss. Okay, we have seen the three methods to calculate the loss. Means these three methods are your basic methods to calculate the loss. Now in the next section what we'll be seeing is, we'll be seeing a perfect loss function, that is universal loss function for the perceptron to determine the loss of the perceptron. Okay, in the first section we have seen the problem with perceptron trick, and in the next section we have seen what is the necessity to introduce the loss functions, and in the third section we have seen the different methods to calculate the loss. Okay, now we'll be looking at a consistent method, that is perceptron loss function, to determine the loss of a binary classifier. Okay, now let's see the formula. Loss function of w1, w2 and b. Now we'll be going with an assumption that we have two inputs, x1 and x2 are your inputs, and the corresponding weights are w1 and w2, and b is your bias. Okay, the loss function of w1, w2 and b means the loss calculated for according to this parameters. Means for this parameters you will have one set of binary classifier line. For next set of parameters you will have another set of binary classifier lines. Okay, based on these parameters, the line you will get, for that line we'll be calculating the loss. Okay, 1 by n means this n determines the number of rows. The n is number of rows. Means will be, if we are having two rows, we will be taking this as 1 by 2 summation of I is equal to 1 to n, 1 to 2. Means for each time the parameters are getting updated, we are calculating the loss. Now let's suppose say for first set of parameters w1, w2 and b, we have gotten binary classifier line. Okay, now what happened is loss is calculated, and by that loss you are doing a back propagation. According for that back propagation you are getting some set of w1, w2 and b values. Now for that new w1, w2 and b values, you are having another binary classifier line. Okay, in this way you how much this n value is there, that many times the loss is calculated. Means if the n is 2, for the first row you'll get some binary classifier and some set of parameters, and the back propagation is done, and the weights are updated, w1 w2 and bias are updated, and they are multiplied to these inputs, and next time loss is calculated. Okay, if it is 2, the 2 times this operation is done. Okay, and loss is calculated between wi, sorry, y is your true output, y is your true output. The loss is calculated between yi and fxi. The fxi is equal to w1 x1 plus w2 x2 plus b bias. Okay, loss is calculated between, means for each row loss is calculated between ya true output and f of xi. F of xi is w1 x1 plus w2 x2 plus bias b. Okay, loss is calculated between this true output and predicted output. Okay, now let's see how loss for individual row is calculated. Now loss for individual row, this is for n number of rows, this is for individual row. Loss for individual row is calculated between yi means true output and predicted output is equal to max, means among these both which is maximum, that will be your output. Max of 0 comma minus of yi. Y is your true output and fxi is your predicted output. Okay, you multiply this both and you apply negative sign. Maximum among them is your loss function, means loss is your loss function output. Okay, now let's substitute this in the above formula and let's rewrite the equation. L is equal to 1 by n summation of I is equal to 1 to n max of 0 comma minus y into y hat. Y hat is your predicted output. F of x I is equal to yi hat. Okay, now let's substitute and value and see how this loss function is working. Okay, now let's see yi is equal to minus 1 or plus 1, means your true output is either minus 1 or plus 1, means this is an binary classifier line. For this it is plus 1, for this it's minus 1. Let's suppose say for this it's plus 1, for this it's minus 1. Okay, now yi hat is calculated as 1 and yi value is minus 1. Okay, means you see that it is wrongly predicted. Okay, now let's calculate the loss function. Let's assume that it is only having a single row, max of 0 comma, now let's multiply both these values, minus 1 into 1 into minus, means you'll have a minus initially. Okay, now minus 1 into plus 1, it's minus 1, minus 1 into minus, it's plus, max of 0 comma 1. Okay, max of 0 comma 1 is 1, loss is equal to 1. Okay, this, okay, you have determined that yi hat value is 0.5. Okay, now how the loss is calculated? Let's suppose say ya value is equal to 1. Okay, ya hat value is 0.5, ya is equal to 1, max of 0 comma minus of yi value is 1 and yi hat value is 0.5. Now let's see the maximum of this equations. Max of 0 comma minus 0.5 is 0, but you see that there's some marginal error between this 1 and 0.5, that is 0.5. 0.5 is your marginal error, but it's unable to determine that marginal error. Okay, this is the main disadvantage with this perceptron loss function, means these kind of marginal errors cannot be determined by the perceptron loss function. So to encounter this, we introduce another loss function, that is hinge loss function. Okay, now let's see how the hinge loss function looks like. Okay, now let's see how an hinge loss function looks like. Hinge loss function L is equal to 1 by n, same, looks similar, is equal to 1 to n max of, just you add an extra term that is 1 before this minus, you add an extra one term that is 1 minus y minus y hat. Okay, this is your hinge loss. Okay, now let's substitute the similar values in this hinge loss function, and we'll be evaluating the output of this and this. Okay, L is equal to, we are calculating only for a single row, so max of 0 comma 1 minus, let's say this is 1 and this is 0 0.5, 1 into 0 0.5, that is max of 0 comma 0 0.5. The maximum of 0 and 0 0.5 is 0 0.5. The loss is determined as 0 0.5. But in the previous case, we are considering your perceptron loss function, the loss you got is 0. Means for that marginal values, you are getting the loss as 0. Even you substitute 0 0.5, you will be getting the value 0. But when you consider the hinge loss function, when you are taking these kind of marginal values between 0 and 1, for the ya value as 1, you see that even the hinge loss is considering the marginal loss values. This helps the model to make confident predictions. Okay, now in this case where the for 0.5, for the 0.5 marginal value of y hat, the model has predicted 0, means that is an unconfident prediction. In that case your model is not performing well, means that is an unconfident prediction. But when your loss is 0.5, the what the model does is, as this is an unconfident prediction, what your model does is it tries to improve the confidence, means strength of the prediction. Okay, it tries to improve the strength of your prediction and gives you best prediction. It adjusts this 0.5, means it always tries to make this as 1. Okay, it tries confidently to make this as 1, but in this case, as it is eventually, means initially it is determining you as 0 loss, but here even it is considering the marginal loss values and trying confidently to make it as correct prediction. Okay, this is the basic difference between hinge loss and perceptron loss. In perceptron loss, you for marginal values like 0 to 1, your perceptron loss fails, but for hinge loss, for even for the marginal values, the loss is considered and helps in making the confident predictions. Okay, these are the different types of loss functions that are used in an perceptron. Okay, now let's see the next section of the video. In the previous section, we have determined two important loss functions, that is perceptron loss function and hinge loss function. The disadvantages in perceptron loss function are overcome by hinge loss functions. In the case of code implementation also, we'll be using hinge loss function. Okay, now what's your task is calculate loss from the hinge loss function and perceptron loss function corresponding to these values -1 and -1, 1 and 1, -1 and 1, 1 and -1, 1 and 0, and 1 and 3. Okay, I'll be explaining for this case 1 and 3. When you substitute 1 and 3 in your hinge loss function, okay, substitute these corresponding values in hinge loss function, loss is equal to max of 0 comma 1 minus 1 into 3. Okay, y value is 1, y I had value is 3. Okay, max of 0 comma you will get -2, that is 0, loss is 0. The maximum 0 and -2 is 0. Okay, the loss is 0. But you may be having some doubt that the ya value is 1. No, ya had value is 3. Okay, you see that the difference between the actual output and the predicted output, means you need to have loss, but this is not an actual loss. It says that this 3 value says that I'm confidently predicting 1 as my output. This 3 determines that I am confidently predicting 1 as my output more confidently. Okay, it tells us the magnitude, how confidently the model is predicting the 1 as its output. Okay, this positive value determines that. Okay, this is one example I given. Calculate for the rest of the values that comes under your intuition section. Okay, now let's see for different loss functions and activation, means combining different loss functions and activation functions, how your perceptron models work on different set of problems. For hinge loss and step activation function, hinge loss is the loss function that I have previously discussed. Step is your initial activation function. In combination of this both, you can use it as a perceptron. That for binary classification, for binary classification task, you can use hinge loss and step activation function in combination. Okay, now for for logistic regression, when you combine binary cross entropy loss with sigmoid activation function, the perceptron can be used as a logistic regression. Logistic regression means classification. Logistic regression is used for classification. Okay, when you combine binary cross entropy loss with sigmoid activation function, the perceptron model can be used as logistic regression. Okay, now when you combine this cross entropy loss with softmax activation function, the perceptron model can be used as multi-class classifier. Okay, means let's say you have dog, cat and tiger. Okay, classifying three different classes is your multi-class classification. Okay, now let's say MSC loss with linear, means mean squared error loss. Linear means no activation function. Linear means no activation function is used for linear regression. Linear regression is nothing but used for examples like house price prediction. Means you have some x label, this is your y is your predicted output. When your graph is linearly going, means linearly it's going up, then it's called linear regression. Means you are predicting the future values, means future house prices. Okay, in that scenarios we use mean squared error loss with linear activation function. Okay, in this way you can alter different loss functions and activation functions from in your perceptron model and use it for different cases. Okay, this is the whole discussion about perceptron loss functions. Okay, hope you like the video. If you like the video, please like, share and subscribe. Thank you.